Now we're back for video 2, where we just talked about work and energy in this simple context where the force of gravity is a constant and the change in potential energy is easy to calculate because potential energy is mgh. Oh, one thing I did forget to mention to the class I was just teaching this to, but I mentioned in the previous video, U is the symbol that a lot of textbooks and the AP tests use for potential energy. They use PE sometimes, but more often than not they use U also. Maybe that's because they believe that you have lots of potential. Okay, but yeah, that was horrible. And I made the same joke in the other video, so it's on there twice now. Look at that. But just now when you see U, that's how they are referring to potential energy. Okay, so let's go to a planetary situation now, where we want to talk about A, how the force of gravity is expressed. B, we're going to look at work first, and then we're going to use that to get to how do you calculate gravitational potential energy or changes in gravitational potential energy when you've got a big planetary scale like this. So step 1, that's really a bad picture. We're going to give that a 6.86 out of pi radical 13. So its spheres are ranked out of. We want to talk about having something fall towards the Earth, but not over short distances, like near the Earth's surface. We want to fall from large distances, from far, far away. So like double or triple the radius of the Earth. So this is, I guess, the distance from here to the center of the Earth is 3 radius of Earths. And this distance from here to the center of the Earth is 2 radius of Earths. Okay. The first thing we want to think about is, how do I calculate that force of gravity that's going to act on this mass m as it falls from this location, which I guess we'll call location A, to B? How do I calculate the size of that force of gravity that's going to be acting on that object? Okay, there was a momentary pause because the class I'm filming this in front of didn't realize that I was not asking a rhetorical question. I actually was asking the question. They totally knew this. So the force of gravity is gmm over d squared, or as some said, gmm over d squared. I like it. Okay. If I wanted to make this into a vector, that force of gravity, what I would say is I would express it as gmm, and instead of doing d, I'm going to measure all my distances out from the center of that planet as r's. So I'd write it as gmm over r squared. I'd put a negative, and I'd do a lot of things. Undo that. Undo that. I'd put a negative in front, and I'd put an r hat at the back. What in the world is that? I've got an r and I put a hat on top of it. Okay, so the negative actually goes with the r hat. R hat is a unit vector, just like as we learned early in the year, I, j, and k are unit vectors. I represents along the x-axis, j represents along the y-axis, k represents along the z-axis. R is a unit vector along a radius. So r hat is just some distance along the radius. Well, the force of gravity isn't directed outward along r hat, it's directed inward. So that's where the negative comes from. The negative is really, this is this size force, gmm over r squared, in the negative r hat direction. Okay. I'll pause the video there and maybe finish it a bit later.